Hello everyone and welcome back to my YouTube channel. This is the second video in our series to create a two-layered artificial neural network without any machine learning library. And in this video, we go over the concept of backpropagation of errors. In the first part of our series, we defined a two-layered artificial neural network with a simplified version of the mean squared error as our cost function, aka loss function, aka error function. We also learned that there are two ways in which the data traverse an artificial neural network. The first way is from the input layer to the output layer, aka forward pass, and the second way is from the output layer to the input layer, aka backward pass, aka backpropagation of errors. In the first part, we have coded our forward pass and we have got some predictions. We made some predictions and we saw that their values were pretty small. As a result, the value of our cost function was quite huge. This indicates that there is a huge gap between our predicted prices of Boston homes and their actual values. And in this video, we are going to make our predictions better by reducing our cost function. A neural network is typically trained over multiple iterations. A training iteration is called an epoch, and during each epoch, there is a forward pass where predictions are made, and a backward pass where the weights of the neural network are updated to make better predictions. Gradient descent is an optimization algorithm used for the backward pass. It aims to find the best possible weight values to minimize the cost function. It requires a direction, which is the gradient of the loss function with respect to the weights of the neural network, and a step size referred to as the learning rate. So the gradient points us in the direction that we need to move in order to reduce the weights, and the step size or learning rate dictates the step that we need to take in that direction. After each iteration, the weights are updated to move in the correct direction by subtracting the step from the original weights. So if the learning rate is too small, the model might need a lot of iterations in order to converge to the global minimum. But if the learning rate is too large, the model might not converge at all. There are three types of gradient descent: stochastic gradient descent, mini-batch gradient descent, and batch gradient descent. In this video, we are going to program a batch gradient descent. The backward part of the term backward pass stems from the fact that the calculation of the gradient descent proceeds backward through the network, starting from the output layer to the input layer. Here is what it looks like in our example. According to the chain rule, the partial of the loss function with respect to wave vector v is equal to the dot product of the partial of the loss function with respect to prediction vector y hat and the partial of prediction vector y hat with respect to wave vector v. The partial of the loss function with respect to prediction vector y hat is the difference of the prediction vector y hat and the corresponding target vector y. Now, this is kind of intuitive because we know that the loss function is the sum of the squared of the difference between each prediction value and its corresponding target value. Now, because the loss function is a scalar and the prediction vector is a 404 by 1 vector, we know that the partial derivative of the loss function with respect to prediction vector y hat should be a vector of shape 404 by 1. And this is where the simplified nature of our loss function comes into play, because we know that the derivative of the squared will get cancelled with the 2 in the denominator. So these 2 and these 2 will get cancelled out when we will calculate the derivative of the square here. So we will be left off with only the difference between the two vectors. Moving on to the next partial, the partial derivative of the prediction vector y hat and the wave vector v is equal to the output matrix z. Now remember, z was the output matrix of the hidden layer. Now this result is straightforward because we know that the prediction vector y hat is the dot product between output matrix z and wave vector v. Putting the two results together, we obtain the partial derivative of the loss function with respect to wave vector v, which is equal to the following dot product. We have just calculated the partial derivative of our loss function with respect to the wave vector of the output layer. Moving down one layer and applying the chain rule, the partial derivative of the loss function with respect to the wave vector of one of the hidden layer's neuron is equal to the dot product between the partial of the loss function with respect to y hat, the partial of y hat with respect to the output of the concerned neuron, and the partial of the output of the neuron with respect to its weight vector. We know from above that the partial of the loss function with respect to y hat is equal to the difference between the prediction vector and the target vector. Similarly to what we saw in the output layer, the partial of y hat with respect to the output of the neuron of interest should be a 404 by 404 matrix. This is because y hat and zj are both 404 by 1 vectors. The resulting matrix is the inner product of the 404 identity matrix and the weight of the output layer's neuron that is multiplied by zj in the dot product resulting in y hat. Now the partial derivative of the neurons of interest output with respect to its weights is equal to the input matrix, where all samples that give a negative dot product with the neuron's weight is cancelled out. So they are all replaced by 0. And this is due to the ReLU function, which essentially cancels the influence of such inputs. I encourage you to write out the loss function and try to compute this partial derivative. If this is still not clear to you, please let me know in the comments if you want me to make a video to further detail these calculations. Putting everything together, we obtain the partial derivative of the loss function with respect to the wave vector of a neuron in the hidden layer. Now that we know how the gradient is propagated back to the first layer, let's get back to our code to compute our backpropagation of errors.